Rokok.
Hi everyone, we are Group 31 from Mayflower University and we are currently studying software engineering. Today we will explore key concepts in data structure and algorithms, focusing on session and sorting. Let me introduce myself. I'm Nanshuzin and my teammates are Chomuse, Intro R, Anjosu and Yemiamin. Thank you for your attention. Let's begin our presentation. Now let's talk about why session and sorting are important in computing. What is session? Session is the process of finding specific data within a collection. It is essential for quickly retrieving target information, whether in databases, search engines, or even your phone's contact list. Imagine trying to find a book in a huge library without catalog. Session helps provide that choice. What is sorting? Sorting is the process of organizing data in a structured order, such as ascending or descending. It makes session much faster and helps in data analysis and decision making. For example, sorting student score in a school system allows quick ranking and evaluation. Without efficient session and sorting algorithms, handling large data set would be slow and inefficient. That's why today we will explore binary search and insert two key algorithms and improve these processes. Now my teammates will explain binary search and insertion sort in detail.
Now let's talk about binary search, a powerful and efficient session algorithm. So what is binary search? Binary search is a method used to find an element quickly in a sorted array. Instead of checking every element one by one, it follows a divide and conquer technique, significantly reducing the number of comparisons needed. Imagine searching for a word in a dictionary. Instead of checking every word from the beginning, you flip to the middle, check where your word might be, and narrow down your search. This makes the process much faster. Binary search is widely used in computing because of its speed and efficiency. In the next slide, I will explore how it works in detail. So, we understand what binary search is. Let's see how this works. Binary search follows a step-by-step approach to efficiently locate an element in a sorted array. We start in the middle of the array, compare the middle element with the target value. If the element is the target, we then. If the target is smaller, we discard the right half and search in the left half. If the target is larger, we discard the left half and search in the right half. We repeat this process until we find the element or confirm that it doesn't exist. Now, let's see how binary search actually works with an example. We have a sorted array 1, 6, 7, 14, 17, 21, and 25. We want to find element 6. The left index and the right index, then dividing the result by 2. So we got left index is 0 and the right index is 6. So the middle could be 3. The element at index 3 is 14. So we have to move. Since 6 is smaller than 14, we ignore the right half, focus on the left half. We now find a new middle index in the reduced range. The left index is 0 and the right index is 2. So the middle index is now 1. The element at index 1 is 6, which is our target. So instead of checking each number one by one, binary search quickly find the answer key, eliminating half of the search space in every step. This makes it much faster than linear search.
Okay, now that we understand how binary search works,
Okay, now that we understand how binary search works, let's look at the implementation. There are two main ways to implement binary search, iterative and recursive. First, the iterative approach. In this method, we start with two pointers, one at the beginning left and one at the end right. We repeatedly find the middle element and compare it with the target. If it is a match, we return the index. If the target is smaller, we move to the left half. Otherwise, we move to the right half. This continues until we find the target or the search space become empty. Now, the recursive approach. Unlike the iterative method, this approach relies on function calls where instead of a loop. The functions keep calling itself with the updated left and right values until a base case is met. In recursion, we always define base cases to stop further calls. Here, we have two base cases. First base case, if the left index is greater than the right, it means the target is not in the array, so we return -1. Second base case, if the middle element matches the target, we return its index, as we have found the element. If neither base case is met, we continue searching recursively. If the target is smaller than the middle element, we search in the left half by making a recursive call. If the target is larger, we search in the right half by making another recursive call. Both approaches have a time complexity of O log n, making them much faster than linear search. Binary search isn't just a theoretical algorithm, it powers many real-world applications, making searches faster and more efficient. For example, looking up a content in a phone book. Imagine flipping through a thick phone book. Instead of checking every name one by one, you jump to the middle, decide if the name is earlier or later, and narrow it down quickly. That's exactly how binary search helps find content instantly. Next is for online store. Searching for a product in online store. Ever wonder how online store suggests products so quickly? Instead of scanning millions of listings, binary search helps filter and locate items efficiently, making online shopping seamless. After that, student scores for database queries. University and schools store thousands of student records. Instead of searching through all data, binary search retrieves the student score in just a few comparisons, saving time and resources. From everyday tasks to large-scale data management, binary search plays a crucial role in making such operations lightning fast.
Okay, let's talk about sorting. Sorting is an essential operation in computing. Among various sorting algorithms, insertion sort stands out of its simplicity and efficiency in small dataset. Unlike other methods, insertion sort places elements one by one in their correct positions. It builds the sorts like gradually, ensures that each new element is inserted when it belongs. Let's imagine organizing a stack of documents in a cabinet. You have to take one document at a time and insert it into the correct alphabetical or numerical order. This is exactly how insertion sort works. The key features of insertion sort include work best when elements are already partially sorted, highly efficient for small data sets, and maintain orders dynamically as elements arrive. So now let's break down how insertion sort works with the step-by-step example. Insertion sort picks each element one by one and insert it into a correct position within the sorted part of that array. At each step, the current element is compared with the left element, and if it is smaller, we shift the largest elements to the right until we find the correct position. As shown in the visualization, the number 12 is compared with 11, which is the left element. As 12 is larger than the 11, we do nothing and put them in each position. Then in the next iteration, the number 3 is compared with 12 and 11, and it moves left until it reaches the correct position. Similarly, 5 is placed by shifting 12 and 11 to the right. This process continues until all the elements are correctly placed in ascending order, resulting in the final sorted array.
Now let's explore how insertion sort algorithm work in the real-world example. Insertion sort works by taking one element at a time and placing it in the correct position within the sorted part of the array. 1. We start sorting from the first element, index 1. 2. The current element is compared with the previous element. 3. The previous element is greater, we shift it to the right. 4. We continue shifting until we find the correct positions. 5. The current element is then inserted at the correct position. 6. The end, the position repeated for all elements in the array. As shown in the code, We look through the array, shifting element as needed, and placing each element in its correct positions. The common example of this sorting method is arranging student score in ascending order, just like we see here. Insertion sort is simple, efficient for small datasets, and work well when elements are nearly sorted. In conclusion, that brings us to the end of our presentation, binary search and insertion sort. To summarize, binary search is a highly efficient searching algorithm that works on sorted arrays. By reliably driving the search rate in half, it quickly finds the target element, achieving the time complexity of O log n. However, it requires data to be sorted beforehand, which is where sorting algorithms like insertion sort come into play. On the other hand, insertion sort is an intuitive sorting algorithm that works by picking elements one by one and inserting them into their correct positions in their sorted portion of the array. If it's efficient for small and nearly sorted datasets, but can be slow for large datasets due to its O_N time complexity in the worst case. Together, these two algorithms demonstrate the importance of sorting and searching. Sorting helps organize data, while efficient searching enables quick data retrieval. Understanding these fundamental algorithms build a stronger foundation for more complex problem-solving techniques. And this is the end of our conversation. Thank you for listening. Do you have any questions?